Hey y'all, welcome back. Today we are reviewing for our Unit 6 test, which is all about the fundamental theorem of calculus with some applications thrown in there. We also spent a good deal of time during this unit getting to know the Desmos calculator, and we've answered a bunch of the free response calculator questions from old AP tests so that we can hopefully become a little bit more familiar with the types of questions that you can expect to see there. So let's get on into it. First, we have the non-calculator portion of the review. We'll save all the calculator problems for the back end so that we don't have to bounce back and forth between using Desmos and not. So number one says evaluate each of the following, show your work. And as we go through these, I'm going to cite whether or not they're from the first part of the fundamental theorem or the second part of the fundamental theorem. I know it's a little confusing because we started out learning about part two, which is what you're going to use for this first problem, the second part of the fundamental theorem of calculus. But the first part of the fundamental theorem is something that we covered afterwards, and you'll use that to answer questions like 1C over here. So I'll try to cite these as we go, and I'll call them FTC2 or FTC1. The numbers there, it doesn't really matter. I just want you to know that both of these types of questions are part of the fundamental theorem of calculus. So the second part of the FTC has to do with finding the value of a definite integral, whereas the first part has to do with finding the derivative of an integral where one of the boundaries is a function of x. So let's do 1a here. To find the value of a definite integral, you need to first find the antiderivative of what's given here, and the antiderivative for cosine x is 4 sine x, and we're going to evaluate that from 0 to pi over 2, meaning we're going to substitute in pi over 2 and 0 into x and then subtract those two values. So 4 times sine of pi over 2 minus 4 times sine of 0. Now sine of pi over 2 is 1, sine of 0 is 0. So this is going to be 4 times 1 minus 4 times 0. So 4 minus 0 equals 4. Part B really is going to be, I guess that's going to be the second part of the fundamental theorem. We're just going to use the antiderivatives to evaluate this. Now we're going to have to plug in x here. Well, you'll see exactly what happens. So the antiderivative of 3t squared plus 2 is going to be, not 6. No, we're not doing derivatives. We're doing antiderivatives. Sorry about that. It's going to be t cubed plus 2t from 2 to x. So if I substitute in x into t, that'll be x cubed plus 2x minus, if I substitute 2 cubed is 8, and 2 times 2 is 4. So I've got x cubed plus 2x minus 8 plus 4. I can combine the two constants to get my expression here. I'm not going to be able to evaluate this. It'll leave it like that. For part C, here is where we're using that other part of the fundamental theorem, and that's when you're finding a derivative of an integral. And remember that those are basically inverse functions. They kind of undo each other. But when you have this upper boundary, we're going to substitute that in to every instance of t. So we have tangent of x over 2 times the tangent of x plus 5. But then we need to multiply by the derivative of that upper bound. So the derivative of tangent, don't forget, you still need to know those trigonometric derivatives, all those transcendental derivatives. The derivative of tangent secant squared. Okay, so there's number one. Number two says the average value. Okay, so average value, we've got a formula for that, of the function f of x over the closed interval 2 to 4 is equal to 3. What's the value of the integral from 2 to 4, f of x dx? Okay, so we are going to use FTC2 here. This is an FTC2 problem. We're going to set up basically, well, we're finding the average value here. Is this going to be an FTC2 problem? Hold up. Actually, let me think for a second. No, we're actually not going to use that. We're just going to find the average value. So the average value is the integral from 2 to 4 of f of x dx divided by 4 minus 2. And it says that that average value is equal to 3. So 4 minus 2 is 2, and I can multiply 2 on both sides to see that the integral from 2 to 4 of f of x dx is 3 times 2, which is 6. And that's all it's asking. That's it. It's 6. I actually really don't need the fundamental theorem there. Part 3, or number 3, says using the table below and the fact that f prime is continuous on the interval 0 to 2, determine the integral of f prime x dx. Okay, so here we are going to use the fundamental theorem. We're going to use that second part, FTC2. And let's rewrite this. 0 from 0 to 2 of f prime dx. That's going to equal the antiderivative of f prime, which is f of 2 minus f of 0. So if I want to find the value of this guy right here, I just need to subtract the value of f at 2 and 0. So f of 2, we can see, is 12, and f of 0 is negative 5. So 12 plus 5 is 17. Number 4 says if capital F is equal to this integration function, then what is f prime? Okay, here we're actually going to use the first part of the fundamental theorem because we need to find the derivative of f. So in other words, we need to find the derivative of the integral from e to x cubed of this weird natural log function. And so we know what to do here. We're going to substitute in this x cubed into t, and that's going to be the natural log of x cubed squared. Anytime you raise an exponent to another exponent, you're going to multiply those exponents. So 3 times 2 is 6. So this will be x to the 6th plus 1. And then we're going to multiply by the derivative of that upper bound, which is going to be 3x squared. I want to make a note here that the lower bound, this Euler's number constant, is not going to affect anything. And we talked earlier in the unit when we first went over this why that is, and it has to do with differentiating a constant that becomes 0. But yeah, so we don't really need to worry about what that lower bound is. And so let's see, do we have this as one of our answer choices? Looks like it's B. Number 5, given the graph of f of x, which consists of a semicircle and 2 line segments, determine the average value of f of x. Okay, so right away I'm thinking average value of f of x between negative 2 and 4. That's going to be the integral from negative 2 to 4 of f of x dx divided by 4 minus negative 2, which would be 6. And so, yeah, we need to calculate the area underneath the curve of f of x between negative 2 and 4. And that's how we're going to calculate this thing. The denominator we can calculate just using arithmetic. 4 plus 2 is 6. That's pretty straightforward. But don't forget that the integral, or a definite integral, is really just asking for the area under that curve. So we have a semicircle here, which is going to be half pi r squared. Pi r squared is how you find the area of a full circle, so it's going to be half that. And the radius here is 2. Okay, so 2 squared is 4. 4 divided by 2 is 2. So the area of this semicircle is 2 pi. The area of the triangle is 1/2 base times height. So half of 2 times 2. 2 times 2 is 4. Half of 4 is 2. So we've got 2 pi plus 2. And that's good. That's a good answer. We could simplify that since both the numerator and the denominator have a factor of 2 that we can cancel out. And so you could write this as pi plus 1 over 3. It's possible if that was a multiple choice question that's what it's going to look like. And if it was a calculator problem, you'd probably need to type that in. But I'm happy with what I have boxed there. Number 6 says evaluate each of the following. The first one is the integral from 3 plus x over x dx. And so we're going to use that second part of the fundamental theorem to evaluate that. So, okay, actually, you know what? Before we get going with that fundamental theorem, let's rewrite this to make finding the antiderivative a little easier. So we can split this up and say 3 divided by x is 3 times x to the negative 1, and then x divided by x is 1. So we're going to think of that function. We're going to rewrite it like that so that we can use the anti-power rule. Okay, so now let's come up with that antiderivative. The antiderivative of x to the negative 1, or 1 over x, is the natural log of the absolute value of x. Don't forget about the absolute value there. So we have 3 times the natural log of the absolute value of x, plus the integral of 1, which is x, from 1 to e. So now we need to substitute those in. If I substitute in e, I'm going to get 3 times the natural log of e. The natural log of e is just 1, so that's just 3 times 1 plus e. Okay, and then plugging in 1 is going to be 3 times the natural log of 1. Natural log of 1 is 0 because e to the 0th power is 1. 0 plus 1. So we end up with 3 plus e minus 1. 3 minus 1 is 2, so this is just going to be 2 plus e. Okay, part B, we're trying to figure out what is f prime of 2. Okay, so since we're going to need to differentiate this integrable function, that's our clue that we're going to use FTC1. Okay, basically what we want is the derivative of this. Okay, and so to find that derivative, we're going to replace t with 2x. So this is going to be 2x over 2x quantity squared. Be careful here, it's 2x in parentheses squared. So if you're going to rewrite that, it's going to be 4x squared. But I'm just going to leave it like that. Times the derivative of 2x, which is just 2. Okay, so this is f prime x, I should say. So if I want f prime of 2, I'm going to substitute in 2 everywhere I see it. So everywhere I see x. So 2 times 2 is 4. And then let's see, 2 times 2 is 4. 4 squared is 16. 16 plus 5 times 2. So f prime of 2 is 4 times 2 is 8. Over 16 plus 5 is 21. Number 7, if the integral from 1 to k of 1 over, okay, well, as soon as I see this, again, I'm going to be rewriting this so that I can see how to integrate it a little easier. So I'm going to rewrite this as, instead of 1 over root x, I'm going to write it as x to the negative 1/2 power. Okay. So anyway, if this is true, then what does k equal? Okay, so we have this integral from 1 to k of x to the negative 1/2 dx. And so we're going to integrate that, or find the antiderivatives of x to the negative 1/2. And that would be x to the positive 1/2. And then dividing by 1/2 is the same thing as multiplying by 2. And we're going from 1 to k. So if I substitute in k, I'm going to get 2 times k to the 1/2, which is really like the square root of k. Just keep that in mind. And then if I plug in 1, I'm going to get the square root of 1, which is 1 times 2 is 2. Now, that's what the definite integral equals. And it said at the beginning that this equals 4. And so this is how we're going to find k. So we're basically going to set up an equation. 2 times the square root of k minus 2 equals 4. Add 2 to both sides, get 2 root k equals 6, divide both sides by 2, so we get a root k equals 3. So if we square both sides, we get k equals 9, and so our answer is C. Number 8 says a continuous function g is defined on the closed interval -5 to 5. The graph of f is shown, consists of 3 line segments, this one, and then this constant over here, and a quarter circle. So this is actually a quarter circle. Let f be the function given by g of x, which is the integral from -5 to x f of t dt. So part A wants to find g of 3. So g of 3 is going to equal that function, except we're going to replace x with 3. So that'll be the integral from -5 to 3 f of t dt. Looking at the graph of f, let's see, -1, 2, 3, 4, 5. First partition's over here, the left partition, I should say. And the right partition is going to be at 1, 2, 3. So let's find the areas of each of these individual shapes. the area of that first triangle is going to be, let's see, 3 times 4 is 12, divided by 2 is 6. So I'm going to think of this area as being negative 6. For this one, it's a quarter circle. So 1/4 pi r squared, where r is 2. So 2 squared is 4. 4 divided by 4 is 1. So that's just going to be pi. The area is pi, but since it's below the x-axis, we're going to call it negative pi. For this little triangle right here, that's a 2 by 1 triangle. 2 times 1 is 2, divided by 2 is 1. And it is below the x-axis, so I'm going to call it negative 1. And then for this last triangle, we've got 2 times 4 is 8, divided by 2 is 4. And that's above the x-axis, so that's a positive area. So yeah, this area is going to be negative 6 minus pi minus 1 plus 4. Okay, 4 minus 1 is 3. 3 minus 6 is negative 3. So this will be negative 3 minus pi. Part B says determine g prime of negative 1. Now, g prime. So g prime, well, let's first write out what g prime is. Okay, so it's the derivative of this thing. And so we're going to substitute in that upper bound x into t, which will be just f of x, and the derivative of x is just 1. So g prime is just f of x. So if I want g prime of 1, that's just going to be f of 1. And so we just need to evaluate the function of f at 1. Okay, in other words, give me the y value when x is 1. So x is 1 right here, and we can see the y value is just 0. So g prime of 1 is 0. Letter C wants the second derivative of g. Now, if we already determined that g prime was f, then g double prime should be f prime. In other words, we want the slope of f. So g double prime of negative 3 is asking for the slope of f at negative 3. So if I back up to negative 3, let's see here, 1, 2, 3, I want the slope of this segment right here. So the slope, since I'm going up 4 over 3, is just 4/3. Number 9 says the height of a tree at time t is given by a twice differentiable function, h, where h of t is measured in meters and t is measured in years. Selected values of h are given in the table below. Part A says use the data in the table to estimate h prime 6. So just to be clear, this is talking about the slope of h, the rate of change of h at 6. Now, we don't actually see 6 in the table. That would be roughly here. So we're going to use the 2 coordinates right around it to estimate that slope. So here's the first coordinate, 5, 6. Here's the second coordinate, 7, 11. So we're just going to use our classic slope formula here. So the difference between the y values, 11 minus 6, over the difference of the x values, 7 minus 5, is going to be 5 over 2, okay, or 2.5. And this is, the units here are meters per year. Now it also says interpret the meaning of that in the context of the problem. So that means that the tree, so here's our answer. Basically, we have an answer, setup, units, and now we have the interpretation, which is that the tree grows, okay, in other words, the height is increasing at a rate of 2.5 or 5 halves meters per year at t equals 6. Okay, really important that on that interpretation piece that you cite the time. Okay, we've seen many problems like this, and we've started to take off points if you don't actually include that time piece to the explanation. Part B says use a trapezoidal sum with 4 subintervals indicated by the data in the table to approximate the average height. Okay, so we're looking for an average height. That's the average value. So let's think about the average value of the height. Would be the integral from, in this case, 2 to 10 of ht dt divided by 10 minus 2. So the trapezoidal sum is what we're going to use to estimate that integral. Okay, since we can't actually find it outright, since we don't have enough information. But we still can estimate it using that data in the table. So yeah, let's start setting up our trapezoidal sums. So this is going to equal, something divided by 8. I'll leave a lot of space here, as usually you need a lot of space. Maybe not so long, so I want to include some units at the end. Okay, so we got 4 intervals. Here's 1 interval, 2 intervals, 3 intervals, 4 intervals. We're using a trapezoidal sum, so we're going to do like a half base times height, or I'm sorry, we're going to find the average of the heights and multiply that by the base. So for the first one, the base length is 1. The second one has a base length of 2. The third one has a base length of 2, and the fourth one has a base length of 3. So to find the quote-unquote height, we're going to average the 2 heights. So here we go. We've got the 2 heights of the first trapezoid are 2 and 1.5. So we have 2, or I guess I should start 1.5. 1.5 plus 2 divided by 2, think of that as like your height, times the base, which is 1. So 1 times that. Plus 2, which is the next base, times the average of the next 2 heights, which is 2 and 6. Plus the base of the third trapezoid, sorry, not 2, but not 2, gosh, not 3, but 2, times 6 and 11 divided by 2. And finally, the last one is going to have a base of 3. The average of the heights are 11 and 15. So there you go. And this is going to be in meters. And if this doesn't have a calculator, don't worry about simplifying this at all. Or even if you do get a calculator, unless it's like a multiple choice question where you have to simplify it, just don't. Save yourself the pain of trying to get that right. You'll save time and potential errors. Number 10 says let f be a continuous function on 0 to 9 that has selected values shown in the table. And it says using a left Riemann sum, okay, so we're going to use the left partitions to determine the heights of each rectangle, approximate the average value of f of x. So this will be the integral from 0 to 9 of f of x dx all over 9 minus 0. And so again, we're going to use the left Riemann sum to approximate this integral. We still have to divide by 9 because we're looking for an average value. But the left Riemann sum the Riemann sum is what you use to estimate an integral that you can't find otherwise. Okay, so let's set this up. We know we're going to have a big old long numerator here divided by 9. We don't have any units here, so we don't have to worry about units. But now let's set up all of our rectangles. So the first rectangle is going to have a base of 2 and a height of 0. Okay, so 2 times 0. The second interval is going to have a base of 3 and a height of 1. And the last one is going to have a base length of 4 and a height of 2.25. And I'm choosing those left partitions to determine the height because it's a left Riemann sum. If it was a right Riemann sum, we would use the numbers 1, 2.25, and 6.25 as the 3 heights. And yeah, there you go. That's good enough. Part B is looking for the average rate of change of f of x. So that's where we're going to have f of, in this case, 9 minus f of 0 over 9 minus 0. So f of 9 is 6.25, f of 0 is 0, and 9 minus 0 is 9. So we have 6.25 over 9, and that's the average rate of change. Number 11, we've got a piecewise function, 3x squared and x. 3x squared is going to be for when x is less than 0, and x is going to be for when x is greater than 0. So just to get a little visual here, we don't have a calculator, but we know the first one is a parabola. So it's going to essentially do something like this. I'm not going to put any numbers on here. I just wanted to give you a general idea of the shape of this piecewise function. And then f of x is equal to x after 0. So it's just going to be this, like a line like that. So this is roughly what the graph's going to look like. Again, just roughly. So it says determine the integral from -2 to 1. So -2 is going to be over here, 1 is going to be over here. And so basically we have to split up this integral because we'll use different functions for different intervals on the domain. So we can use 3x squared. So in other words, I'm going to use 3x squared from -2 to 0, right? So basically from here to here, and we're interested in this area, plus the integral from 0 to 1. That's this area of x. Okay, so the antiderivatives of 3x squared is going to be, what would that be? Just x cubed plus c. I'm just going to leave it as x cubed. We know the plus c's are going to cancel out from -2 to 0, plus the integral of x is x squared times a half. So 1/2 x squared from 0 to 1. Now, you really don't need to do this second integral like this. Because it is a basic shape, we could just use the triangle formula, 1/2 base times height. But since I already wrote it down, we'll just roll with it. So for the first one, if I plug in 0, I just get 0. Okay, and if I plug in -2, I guess I don't need these brackets. This is just a single term. If I plug in -2, -2 cubed is -8. So I have 0 minus -8. So that's going to really be 0 plus 8. And then for the last one, I've got 1/2 x squared. If I plug in 1, 1 squared is 1, times a half is just a half. And if I plug in 0, I'm just going to get 0. So I have 8 plus a half, which would be 8.5, or we'll call it 8.5. Part B says, what is the average value of f of x on the closed interval -2 to 1? So average value is going to be the integral from -2 to 1 of f of x dx divided by 1 minus -2. Now, we already calculated the integral from -2 to 1. We did that over in part A. So we know that's going to be 8.5 divided by 1 minus -2 will be 3. Yeah, that's it. Number 12 says determine the derivative of this function. Okay, so we've got that derivative of an integral. That's our indication. We're going to use FTC1. We're going to substitute in 2x everywhere where we see t. So this is just going to be e to the 2x plus 2 times 2x. And then that whole thing, be careful that we do need to multiply the entire function by the derivative of 2x. So the whole thing is times 2. And don't worry about simplifying. 13 says f prime is 3x squared and f of -1 is 2. Then what is the integral of f of x from 2 to 0? Okay, so I guess we're going to have to set up a fundamental theorem here, but we're going to have to do a little work to fill in some of the pieces. Okay, so the fundamental theorem says that, well, the integral from 0 to 2, let me erase this real quick. No, that's fine. From 0 to 2 of f of x. Now, we don't know what f of x is yet, although we do know that f of x is the antiderivative of f prime. So since f prime is 3x squared, the antiderivative of that would be, what would that be? X cubed divided by 3. So yeah, so x, it would be, well, hold up. We need to figure out what that antiderivative is. Let's back this up. Let's not start with, we will need to use that fundamental theorem, but let's take a moment to find that antiderivative. So that means that f is going to be x cubed plus c. We need to figure out what that c is to be able to answer this question. And so to do that, we use this other point that we found, f of -1 is 2, to say, okay, well, if f of -1 is 2, that means 2 equals -1 cubed plus c. -1 cubed is -1, so we have 2 equals -1 plus c. And if I add -1 to both sides, hold on. negative 1. I want to add 1 to both sides. So that'd be 3 is c. So if 3 is c, that means that f of x is actually x cubed plus 3. Okay, so now we can actually go back and do what we're going to do. The integral from 0 to 2 of f of x dx is going to be equal to the integral from 0 to 2. Now that we know what f of x is, we can just fill that in. X cubed plus 3. Make sure we got parentheses on there before the dx. And yeah, now we can just evaluate this like we normally would. So the antiderivative of x cubed plus 3 would be 1/4 x to the 4th. Yeah, plus 3x from 0 to 2. Plugging in 2, let's see, we got 2 to the 4th would be, I'm going to count here, 2, 4, 8, 16. But then I have to multiply by a 4th. 16 divided by 4 is 4. Plus 3 times 2 is 6. So this is what I get if I plug in 2. And then if I plug in 0, I'm just going to get 0 plus 0. So our answer is 10. Number 14. Ooh, this is a multi-step problem. All right. The graph of a function f consists of 3 line segments. So we got one here, here, and here. G of x is given by this function. Oh, almost left the dt off there. Okay. And so first it wants g of 4. All right, so g of 4 is going to equal 3 plus the integral from 1 to 4 f of t dt. So we're actually going to need to find the area under the curve between 1 and 4. So it's going to be like from here to here. All right, so that first shape is a trapezoid. So let's figure out what that would be. Base length is 1. So 1 times the average of the heights, which is 1 and 4. So 1 plus 4 divided by 2. So that'll be the area of that first one. The area of that second triangle, okay, this one right here, is going to be half base times height. Base is 1. Height is 1. So it's just going to be a half. And then for that last one, that's the same triangle. So actually, we're going to have plus a half minus a half. All right, so we got 3 plus 5 halves, and then plus a half minus a half is nothing. So since 5 halves is 2.5, we got 2.5 plus 3. 2.5 plus 3 is going to be 5.5. Part B, find the instantaneous rate of change of g with respect to x at x equals 1. This is kind of a long-winded way of saying we want g prime of 1. Okay, it's been a while since I worded a question quite like that, but when you see that instantaneous rate of change, that means derivative. Okay, so let me just make a note of there. Instantaneous rate of change, that's a key phrase that's saying, hey, find the derivative. All right, so let's find the derivative of g. So g prime is going to be first the derivative of 3, which is just 0. And then the derivative of the integral from 1 to x f of x is f of x. I think I misspoke. It is f of x, but it's the integral from 1 to x of ft dt. So yeah, it is going to be f of x. Okay, so if I want g prime at 1, that's going to be just f of 1, and I can see on the table that f of 1 is 4. So g prime of 1 is 4. Let me erase some of this stuff, kind of clean up this diagram here. Part C says find the equation of the line tangent to the graph of g at x equals 2. Okay, so our setup here, we need a slope. We need a point. Let's start with the point. Since it's called point-slope form, probably makes more sense to start with the point. So we need a point, we need a slope, and our equation is going to take this form. Y minus y1 equals m times x minus x1. Okay, so the point is at when x is 2. Okay, so we need to find the y value of that point. And to find the y value, that's going to be g of 2. Okay, this y value is g of 2. So let's evaluate g of 2. G of 2 is 3 plus the integral from 1 to 2 f of t dt. So that's 3 plus the area from 1 to 2. Now we already found the area of this trapezoid. It's 2.5. It's 5 halves. So we'll just call it 2.5 because arithmetic's a little easier with decimals there. And so that's going to be 5.5. So 5.5 is the y value of that point. Now the slope is going to be the derivative of g at x equals 2. Okay, so the slope is going to be g prime of 2. So let's evaluate that. G prime of 2 is going to be, and we found g prime of x up here, it's just f of x. So that's just going to be f of 2. Let's move over this equation a little bit. Have a little bit more room, or I'll just rewrite it later. So we can see but from the graph that f of 2 is 1. So g prime of 2 is 1. Therefore, the slope is 1. And now we have a point. We got the slope. Now we can write our equation. Y minus 5.5 equals 1 times x minus 2. Part D wants g double prime of 1.5. Now we've already established earlier on part B that g prime of x is f of x, which means g double prime of x is the slope of f, or the derivative of f. And so we're going to be looking for the slope of f when x is 1.5. So I go over to 1.5, which is right here. And so I basically want the slope of this line. Now my rise over run, or my change in y over change of x, is going down 3 and over 1. So the slope is negative 3. Where's the rest of the questions? Hang on, I'm having a little technical difficulties. I'm going to pause this video and see if I can refresh this. All right, and we're back. Sorry for the technical difficulties, although it just probably went by in just a second for you. Number 15 says, if f and g are continuous functions such that g prime is f, so another way to interpret that is that g is the antiderivative of f, then what is the integral between 2 and 3 of f of x dx? So here we're going to use FTC2. The integral from 2 to 3 of f of x dx is going to equal the antiderivative, which in this case we just said was g. So g of 3 minus g of 2. And is that it? That's it. Okay, not much to that problem. Number 16 says, if capital F of x equals this integral, first determine f of 1. So we're going to replace x with 1, which will be the integral from 1 to 1 squared is, well, that's just 1. Okay, so the integral from 1 to 1, we know what's going to happen before we even finish writing this. Anytime you're finding a definite integral and both boundaries are the same, there will be 0 area in between two partitions that are identical. So this is just going to equal 0. Now, if we want f prime of 1, this is where we're going to use FTC1. We're going to differentiate that integrable function. So the derivative there is going to be, well, let's just write it out. F prime of x will be the integral of 3 plus x squared squared, which would be x to the 4th. And then we need to multiply by the derivative of x squared, which is 2x. So if I want f prime of 1, I'm going to substitute in 1 everywhere where I see x. So that'll be the square root of 3 plus 1 times 2. Now 3 plus 1 is 4. The square root of 4 is 2. 2 times 2 is 4. Number 17, the graph of f, consisting of line segments as shown in the figure below. Let g be given by this function. Determine the intervals on which g is increasing. Okay, in order for g to be increasing, that means g prime must be positive. Okay, and then we want to justify our answer. So we need to know, where is g prime positive? So first, let's establish what g prime even is. So if g is the integral from -2 to x of f t dt, then g prime will be the derivative of that integrable function. So substituting in x into t just gives me f of x. So g prime is f of x. And so we want to know, when is g of x increasing? Well, g of x is increasing when g prime is positive. And if g prime is f of x, we want to know, when is f of x positive. And we can look at this graph and see pretty clearly when it's going to be positive. It's going to be positive when it's above the x-axis, which is all of this. So the intervals will be between -2 and 1. And then what is that? 1, 2, 3, 4. So 4 to 8. And my reasoning is because on those intervals, g prime is positive. Part B says, determine the values for x for which g has a point of inflection. Okay, in order for g to have a point of inflection, the second derivative must change sign. So if g prime is f of x, then g double prime is f prime. So if we're looking for a point of inflection, which is where, in this case, f prime changes sign, we're looking for where the slope changes sign. So where does the slope change from being positive to negative, or vice versa? Well, the slope is negative here, and it continues to be negative, but then it switches over to be positive. So f prime is changing sign right here, and it's positive, positive, positive. We're talking about the slope here. The slope is positive until this point, in which case the slope changes to be negative. So there's actually going to be 2 points of inflection. Okay, so the values for x are going to be 2 and 6. So at x equals 2 and x equals 6, there are points of inflection, okay, because at those points, g double prime, which, just a reminder, is f prime, changes sign. Okay, part C says, determine the values for x where g of x has a relative maximum. Okay, relative maximum is when the slope of that function is going to change from being negative to positive. In other words, g prime needs to go from being negative to positive. And as we said earlier, g prime is just f of x. So if we're looking at the y values of f of x, we can see those values are changing from being negative to positive right here. So just as a little aside, since f of x is changing from positive to negative at x equals 1, that means that g would have a relative minimum there. It's not asking for a minimum, but I think it's worth mentioning. So so the values for x is just going to be at that x equals 1. And the reason why our justification here is because g prime, which again is f of x, goes from being negative to positive. It would be enough to just say g prime here, but it's kind of nice to say, well, how do you know that? Okay. Number 18 says, given that f of x equals the integral from 3 to x of t squared minus t minus 12 dt, determine each of the following. So part A says, for what values of f is f of x decreasing? Okay, so if f of x is decreasing, that means f prime needs to be negative. The slope of f needs to be negative. So let's find, if this is f of x, let's declare what is f prime. So f prime is going to be the derivative of this. And when we differentiate an integrable function like this, we're just going to take that upper bound and plug it into t. So that'll be x squared minus x minus 12. Let's see here, x squared minus x minus 12. And we want to know when is that negative. So what we need to do is find the critical points, okay? And we can find those critical points by setting the function equal to 0, factoring, and this would factor as x minus 4 times x plus 3. Got it all nice and factored here. So my critical values are going to be at x equals 4 and x equals negative 3. So those are the x values for which f prime could potentially change sign. So we're going to use some representatives here to plug into each interval and find out whether or not f prime is positive or negative in these intervals. So like if I plug in a number, say like negative 10, I'm going to have a negative times a negative, which is positive. If I plug in a number like 0, I'll have a negative times a positive, which is negative. And if I plug in a number like 10, I'm going to get a positive times a positive, which is positive. So if we're looking for where f prime, for where f is decreasing, or in other words, where f prime is negative on the interval negative 3 to 4. Okay, our justification is because f prime is negative there. Part B says, for what values of x does f of x have a point of inflection? So a point of inflection means that f double prime needs to change sign. So we need to find f double prime. We know f prime is x squared minus x minus 12, so f double prime is going to be 2x minus 1. And that's only going to have one subcritical value. So 2x minus 1 equals 0 means that x is going to be 1/2. This is going to be what I'm calling a subcritical value. So on my number line, I'm going to place 1/2 on there and substitute in numbers to the left and to the right of it to figure out if we change sign here. I'm guessing we probably do because the function's linear, so it kind of has to, but always good to just double check and make sure. If I plug in a number like 0, 2 times 0 minus 1 will be negative. And if I plug in a number like 10, I'm going to get a positive. So I for sure change sign there. So, so the x value, where the point of inflection is, so I'm going to say a point of inflection at x equals 1/2 because f double prime goes from being, well, we don't have to actually say that it's going from negative to positive because it doesn't, as long as it's changing, that's good enough for those points of inflection. So f double prime changes sign. Okay, that's about it for the non-calculator section. And I think this, you're going to see if you work through this review that the test is going to be very similar to this. Obviously, it won't be the exact same questions or anything, but the concept should be the same. So if you feel pretty confident with all the problems that you've seen here on the non-calculator section, you're going to be just fine on the test. So now let's take a look at the calculator section. So I'm going to have to pull up Desmos here before I get started, and yeah, then we'll work through it. So I'm going to just pause this real quick, pull up Desmos, and then I'll be right back. All right, we're back, and I got Desmos up. Number 1 says a tank contains 125 gallons of heating oil at time t equals 9. During the interval 0 to 12 hours, heating oil is pumped into the tank at a rate. Okay, so it's being pumped into the tank. Oil being pumped into the tank. This is pumped in. And we have this function h to define that rate. And this is a rate function. It's in gallons per hour. So if we find the antiderivative of that function, it'd be gallons. And if we find the derivative of that function, it'll be gallons per hour squared. During the same time interval, heating oil is removed from the tank. So we got oil being removed from the tank at this one. So this is being removed. Part A says how many gallons of heating oil are pumped into the tank during the time interval 0 to 12. Okay, so what this is asking, this is one of our net change problems. how many gallons of the oil are pumped into the tank. So we want to know what's the net change in heating oil in the tank during this interval. So to find this net change, we're going to once again rely on finding the integral of, or a definite integral of this rate function. So we're going to find the integral from 0 to 12 of h of t dt. And whatever that equals is going to be our answer. So let me open up Desmos for you. And first I'm going to type in the h function so I don't have to keep typing this expression over and over again. So it's h of t equals 2 plus 10 over 1 plus the natural log of t plus 1. You just look over that, double check, make sure that looks good. Yeah, and that's in gallons per hour. Okay, so and the interval we're interested in here is 0 to 12. So let's go from 0 less than or equal to t less than or equal to 12, so that we only see the interval that we're interested in. We may not really need the graph at this point, but I'll zoom out just so you can kind of see what we're working with. Okay, so yeah, now we want to find the integral from 0 to 12. So we're going to type int for integral, 0 to 12, and now we don't have to retype h of t, we can just say h of t dt. And so we get approximately 70.570. I'm just going to cut off the decimal there, and the units here in gallons. Okay, it is gallons of oil, but what I found is that you really just need to focus on that unit and not necessarily exactly what it is. If you write gallons of oil, that's great, but it's also okay on the AP test to be a little bit more brief and just state gallons. Okay, part B says, is the level of heating oil in the tank rising or falling at time equals 6 hours? So if it's rising, that means that oil is being pumped in faster than oil is being pumped out. If it's falling, that means that the oil is being removed faster than it's being pumped in. So what we need to do is figure out whether or not the difference between the pumped in and removed rate functions is positive or negative. In other words, is that going to be increasing or decreasing because that rate is positive or negative. So the overall rate is going to be the amount being pumped in, that's our h of t, minus r of t. Okay, so it's a rate being the oil getting pumped in, and we're going to subtract all the oil coming out. So to find this rate, we're just going to substitute in 6. So we'll have h of 6 minus r of 6. And I'm going to go start typing this in. This is the first one where we have to reference function r. So I'll go ahead and type that in. R of t is 12 sine of t squared over 47. Yeah, that's it. And I think I'll change the color just so we can see them a little better. There we go. And let's throw on that time interval, that domain restriction. Okay. There we go. Oh, there we go. Okay. So now we can just type in exactly what we wrote down, which is h of 6 minus r of 6. And it's negative 2.924. And the units here are going to be in gallons per hour because this is a rate. And so what this is giving us is the overall rate of change of the amount of oil. And since it's negative, that means that the oil is being removed faster than it's being pumped in. Since this is negative, that means the rate or the amount of oil in there is decreasing. Okay, so the level of oil is going to be falling at time equals 6. So we can just say basically that our answer is falling because h of 6 minus r of 6 is negative. Okay, another way of saying that too, instead of h of 6 minus r of 6 is negative, if you're trying to describe what's happening and put a little context around your answer, what might make more sense is to say that there's more oil being removed than being pumped in. And if we rearrange that inequality and say, okay, well, the amount that is being pumped in is less than the amount that's the rate at which it's being pumped out, then this would be an acceptable answer as well. And I kind of like that answer better. I think it communicates what's happening a little bit more clearly than the other inequality. But you don't have to write it like that. I just want to throw that out there in case that helps it make more sense to you. Number 2 says if f is the antiderivative of x squared plus over 1 plus x to the fifth, such that f of 1 equals 5, then what is f of 4? And so this is going to be another fundamental theorem problem. We're going to set up a fundamental equation, and we're going to basically set up that second fundamental theorem, which says that the integral from a to b, and the a to b that we want to use are going to be these boundaries 1 and 4 of that function, so of x squared over 1 plus x to the fifth dx is equal to f of 4 minus f of 1. And we can set that up because it says that f is the antiderivative of that expression. So over here in Desmos, let's just take a quick look and see what that graph looks like. We've got x squared over 1 plus x to the fifth. And so, yeah, it's kind of hard to see exactly what's happening here. We're going between 1 and 4. So, let's throw in x equals 1 and x equals 4 so we can see where those boundaries are going to be. Just changing the colors here, make this a little easier to look at. This is kind of an odd, let's zoom in a little bit here. Can we see it better? I think that's about as good as we're going to get. So really what we're interested in here is the area underneath this curve, right? And that's what we're trying to find. And so if I call this function f, then I can say, all right, we want the integral from 1 to 4 of that expression. And you could have just typed it in, but I wanted us to be able to see what that graph actually looks like. So we get 0.375. And that's going to equal f of 4, which is what we're trying to find, minus f of 1, which is 5. So to get f of 4, we're just going to add 5 to both sides. And so we get f of 4 equals 5.375. We don't have any units here, so that's going to be our answer. Number 3 says let capital F be an antiderivative of that function. If capital F of 1 equals 3, then what's capital F of 9? So this is basically the same kind of question. And we'll set it up in a very similar way here. The integral from 1 to 9 of natural log of x, quantity cubed, over x is going to equal f of 9 minus f of 1. So let me go ahead and delete the equation from last time. There we go. And now we're going to type in the integral from 1 to 9, the natural log of x. And as I'm typing this, I'm realizing I did not write down the dx. So I'll have to go back and throw that in. Now, if you forget to write it down, what's kind of nice in this calculator section is, got an extra 3 in there. is it won't actually do the computation without that dx. It must have the dx. The way it's programmed is it's looking for the dx to know which variable to integrate with respect to. So let me make a little room for my dx in here. There we go. And then when we type dx, we're going to get our answer. So, well, not our final answer, but we're going to get that integral. We're still solving for f of 9, so we're going to replace f of 1 with what f of 1 equals, which is 3. And once we add 3 to both sides, we got f of 9, which is going to be 8.826. And they must have rounded up, which is fine. We're going to find our answer is letter A. Number 4 says insects destroyed a crop at a rate of this per tons per day, where time t is measured in days. To the nearest ton, how many tons do the insects destroy between 7 and 14? So if we want to find the number of tons that the insects destroyed during that time, that's another net change problem. So we are going to use that fundamental theorem. So we want to find the net change of this function between 7 and 14. Okay, so there's our setup, and we can just type that in directly. We should be able to get our answer. So let's delete this one, start typing away. Oh, looks like I didn't get the 1. That's not 7 to 4. That should be 7 to 14. There we go. So the integral from 7 to 14 of 100e to the negative 0.1t over 2 minus e to the negative 3t dt. Yep, and yeah, this is going to approximately equal 124.994, and so the closest, or the closest number here is going to be D. Number 5. Let f be a function defined on the closed interval negative 3 to 4 with f of 0 equals 3. The graph of f prime, the derivative of f, consists of one line segment, a semicircle, and a semicircle, as shown below. Find f of 4, show the work that leads to your answer. So this is going to be a very similar question what we just worked out. So let's set it up in the same sort of way. The integral of f of x dx from 0 to 4 is going to equal, well, let's call it f prime, sorry, is going to equal f of 4 minus f of 0. So we're looking for f of 4, and we are going to be able to find this integral here by looking at the area bounded by the curve and the x-axis on the graph. And f of 0 was given, right? That's just 3. So the challenge here is just going to be finding that area. So we're going from 0 to 4, and that's from right here to right here. And what we have here is a semicircle that's been cut out of a rectangle. So the rectangle here is a 4 by 2 rectangle. So the overall area of that rectangle I've got shaded in there. Maybe I'll shade this in to kind of help. Okay, that area is 8. Right? And then the area of the circle on the inside, I'll shade this with a little bit of blue. Imagine we're cutting out this piece. The area of that piece is going to be half of that of the circle. So half pi r squared would be half times pi times the radius here is 2, so times 2 squared. 2 squared is 4. 4 divided by 2 is 2. So the area is going to be 2 pi. So we've got 8 minus 2 pi. 8 minus 2 pi is going to be the area highlighted still here in yellow. And that's going to be the area bounded by the curve, which is, with all these colors, kind of hard to see now what the actual curve is. Let me go ahead and draw it in dark black here. This is the curve, and we're looking for the area between -4, so like here and here. And that's going to be 8 minus 2 pi. So 8, well, actually, I take that back. It's going to be 2 pi minus 8 because all that area is below the x-axis. So it's like the opposite of 8 minus 2 pi, which is just 2 pi minus 8. So f of 4 is what we're looking for, and f of 0 is 3. And so when I add 3 to both sides, I'm going to get f of 4 is 3 minus 8 plus 2 pi. 3 minus 8 is -5. So f of 4 is 2 pi minus 5. And we didn't really need a calculator for that. I suppose if this was a multiple choice question, that all the answers, if this was on a multiple choice section of the AP test, and then they'd all be in decimal format, and you'd have to type that in. But I'm fine just leaving it the way it is. Number 6 says an object traveling in a straight line has position x at time t. If the initial position is x is 2, and the velocity of the object is the cube root of 1 plus t squared, what's the position of the object at time equals 3? Okay, so we have this initial position. We have an equation for the velocity. We're interested in the position at a time that's different than the one that was given. So we're going to set that up like we did number 5, like we did number, not like we did number 4, but number 5, 3, 2, yeah, so 2, 3, and 5 are set up in the same way. And that's with that fundamental theorem. So the integral from 0 to 3 of vt, which is the cube root of 1 plus t squared, dt is equal to the antiderivative of velocity, which is position. So that'll be x of 3 minus x of 0. So this piece I'll need to throw in the calculator. X of 0 is given. We just need x of 3. So let's go back to the good old Desmos here and delete this last one and type integral from 0 to 3 of the cube root. Now to do cube root, you might be able to, I don't even know if there's a cube root function in here, but it's probably easier to just type it as a rational exponent. Taking the cube root of something is equivalent to raising it to the 1/3 power. So we'll write it like that. And there you go. So that value is 4.511. That represents a net change in position, equals x of 3 minus 2. So if I add 2 to both sides, I can get x of 3 is 6.511. And they probably rounded up on that integral, so that's why the thousandths place is off by that 1 decimal place. So our answer is D. All right, number 7 says the temperature of a metal is dropping at a rate given by the function g, where g is measured in degrees from t equals 0 minutes to 10 minutes. And the metal is initially 100 degrees Fahrenheit. Part A says, what is the temperature to the nearest degree after 6 minutes? So first, let's start with the original temperature of the metal, which was 100 degrees. And then the temperature is dropping at a rate given by g of t. Now, to find the net change in temperature, we need to integrate g on the interval that we want to know, how much is it actually changing. So it's dropping, so we're going to subtract whatever we have there. So 100 minus the integral from 0 to 6, because we want to know what's the temperature after 6 minutes, of g of t dt. And this is going to be what we type in the calculator. Really, the only difference is for g of t, we're actually going to type in the 10 times e to the negative negative 0.1 t. So let's go over to Desmos here, open this up, and delete that last one. Let's zoom out a little bit. I don't even know if we probably don't even need the graph here, but let's go ahead and type this in. So we want 100 minus the integral from 0 to 6 of gt, which is 10 times e to the negative 0.01 t dt. And there we go. So we get 54.881 degrees Fahrenheit. Part B says, what is the average rate? So we're looking for an average rate at which the temperature is dropping throughout the 6 minutes. So since the function we're given, is it the rate function? This is a little deceiving. We want the average value of the rate function. That is the average rate at which the temperature is dropping. In other words, the average value of this rate function. So to find that average rate, we're going to integrate from 0 to 6, gt dt, and divide that by 6 minus 0. So over here, actually we can keep this piece. Right, that's going to be that net change, but we're going to divide it by the 6 minutes that we're the 6 minutes as the length of that interval. So we get 7.519 degrees Fahrenheit per minute. And that brings us to the last problem of the review. It says the velocity of a particle moving on the x-axis is given by v of t equals 3 plus 2 sine t squared divided by 2. For t values between 0 and 7, the velocity of the particle is measured in meters per second. Show your setups and include units. It's going to be key here. On the free response section, you do have to both show your setup and include units. It also says that t equals 0, the particle has a position of 5 meters. I imagine that's going to come into play if they ask us about the position at any other time. So part A says, what is the velocity at t equals 3? All right, well, the velocity at t equals 3 can be given by just v of 3. This is what we're going to type in to Desmos once we've defined in Desmos what v of t is. So we're going to delete this one from the last problem. We're going to define v of t and just type in the equation exactly how it looks. So 3 plus 2 times the sine of t squared over 2. And so we're interested in v of 3. And v of 3 is 1.044 meters per second. So we got the setup, the answer, and the units. We got everything we need here. I'm not going to box anything here because we kind of already have boxes and it looks a little cluttered anyway. So I'm just going to leave it written like that. Part B says, what is the total distance traveled on the interval 0 to 7? Total distance, a little different from displacement. With total distance, we want all of the distance to be considered positive. So when we integrate the change function v, we need to ensure that all those outputs are positive. So we're going to put absolute value bars around the velocity. And we want to know what's the total distance traveled between time equals 0 and time equals 7. So this is something that we can just type in, just like that. The integral from 0 to 7 of the absolute value of the velocity function dt, which means with respect to t, is 22.545 meters. Letter C says, what's the acceleration at t equals 4? Okay, so the acceleration is the derivative of velocity. So we want the derivative of velocity at 4. You can define acceleration in Desmos, but you don't really have to. You can just kind of stick to velocity here so that you don't have to type anything else. And just type in v prime of 4, and Desmos can handle that, which is pretty nice. It'll look exactly like this, v prime of 4, and there you go. That's it. So it's negative 1.164, and the units for acceleration will be meters per second squared. Part D says, what's the average velocity? So the average of the velocity function on the interval 0 to 7. So we'll take that definite integral from 0 to 7 of the velocity function with respect to time and divide it by the length of that interval, 7 minus 0. Now we can go back, and I guess we haven't done that yet, so I'll just go ahead and retype it. The integral from 0 to 7 of dt, all that divided by 7 minus 0. What am I missing? Oh, no parentheses around the second t there. So it's 3.220 meters per second. Make sure you write that 0 there. If you just leave it, if you don't write anything there, then it looks like you're rounding to 2 decimal places instead of 3. You want to be careful with that. Part E says, what's the displacement? So displacement is the net change in distance. Anytime you want a net change, you need to integrate a rate function. The rate function in this case is velocity. So we're going to integrate the velocity function with respect to time on the interval 0 to 7. And we already have that here in Desmos for the most part. I'm just going to copy and paste this, if it'll let me, and paste it down here. And I guess I need that dt. So this is going to equal 22.545 meters. Finally, what is the position of the particle at t equals 7? So to find this final position, we're going to take our initial position. So I'm going to say v, this is going to equal the initial position, which, what was it again? The t equals 0, the position is 5 meters. So that's our initial position plus the net change in position from 0 to 7. And that's exactly what we had before, but we just need to add 5 to it. So we get 27.545, and that's going to be in terms of meters. Whew. All right. So yeah, you can expect that your test is going to be very similar to what we've seen on this review. There will be a calculator section and a non-calculator section, but there really won't be too much that's really outside of any of the concepts we've talked about on here. I think there's enough of enough of the fundamental theorem here. Enough you have to know enough from the whole year to be able to be successful in a lot of these problems. That don't expect me to throw in some extra trips or traps or anything like that. If you have any questions, please reach out. You guys know you can see me before school. If you need some extra tutoring, you need some help, some one-on-one time, please reach out. Otherwise, you'll have a great day, and I'll see you next time.